Do the start. Okay, let's start the session. So far in the homework 2, we solved the first 5th question, and now we are going toward the 6th question, the question number 6. Question number 6 tell us that, again, in the same kind of like situation, we have a candy box with 12 pieces of candy, and we have 4 flavors and 3 pieces for each flavor. Okay, and it's arranged in a random pack. In this question, we draw 4 times from that 12 candy. Okay, so we draw 4 candy out of that 12 candy. And now in part A, we want to see what is the probability of all those draw are in the same flavor. Okay, so the part A is quite simple. If you go through the question itself, you could easily answer that. We have 3 pieces for each flavor, and if the condition is that the 4 candy we draw having the same flavor, basically means it's impossible. Is that clear? I think it's very straightforward. And what is the probability? What is the word impossible in terms of probability? Means 0. So probability of the event F1, which is all the flavor of the 4 candies are the same, in this question is going to be equal to 0, indicating it's impossible to have 4 similar tastes when each flavor only have 3 elements. Is that clear? Are we good? Okay. The second part asked us that, let's say we have an event F4. We draw the 4 flavor, the 4 candy. Sorry. What is the probability that all of them are different flavors? So we draw 4 candy out of the 12. We know we have 4 flavor, and each flavor has 3 elements, 3 candy. Okay. Now we wanted to see what is the probability that we draw 4 different flavor in our experiments. Yes, actually, one of the way that you could do that is actually the same process that we went with the part B of question 5. Okay, but I want to add another comment into this question. Go on. You could use combination. We are going to go over that in part C, how to use combination. But yeah, that's another way to calculate the probability. Now, any other question? No? Okay. In our experiment, we draw 4 times, and as we talked, it's like we having 4 events in a sequence, 4 tests in a sequence. And we want to see what is the result of the test. Okay, so using our first step that we had in our sequential probability, okay, we could say that, okay, if we have 4 events, okay, we could draw the tree diagram and see what's going to be the possibility of each draw. Okay, since the first draw is kind of like the we don't have anything to compare with in regarding different flavor, so having a different flavor doesn't mean anything in the first draw. So probably whatever we choose in the first draw is going to be unique flavor. Correct? So it's a certain situation that in first draw, okay, we have a unique flavor. So when we say certain situation, it's automatically translate to probability equals to 1. Okay, so in our tree diagram, we have our first draw, and since there's a certainty of having a unique flavor, the probability is 1. Now, when we wanted to like do the second draw, It could be same flavor or one of the other three flavor. Make sense? Now, how many candy remains in our basket after first draw? It's 11, right? And we don't want to pick the same flavor that we picked in the first draw. So our desired situation is the other three flavor that we didn't pick from. How many candy exist in other three flavors that we didn't pick from? Each of them has three candy, each flavor, and we have three flavors. So we still have 9 elements in our basket of 11 candy that could be our desired target. So the chance of us picking a different flavor in our second draw is 9 candy out of the 11 remaining candy. Make sense? So we have 9 over 11 chance of picking a different flavor in the second draw, meaning 2 over 11 is the chance of picking same flavor. We already gone that in previous question. Why is 2 over 11? So it's quite clear. Same process goes to the third draw. In the third draw, now we have 10 candy because we picked 2 of them already. We have 10 candy in our basket. 2 of the flavor are already picked. We want to have the third flavor. Okay. Now in our 10 candy, we have 2 flavors that we didn't pick yet, and each of them have 3 elements in their category. So we have 6 candy that could be answer to our condition out of the remaining 10 in our basket. Okay, so picking the probability of having different candy in a third draw is going to be 6 over 10. Make sense? With the same logic as before, picking a similar candy for the third draw is going to be 4 over 10. With, again, same probability, we could calculate the fourth draw. Picking a different flavor is 3 over 9, and having a similar taste is going to be 6 over. So now that we have the probabilities of each of the events of our sequence of 4 draw, through the rules of sequential probability, we know that the probability of the overall situation is the multiplication of the probability of each stage, if each test. So the probability of having 4 different flavors when we draw randomly from our basket is going to be draw number 1 multiplied by the probability of draw number 2 multiplied by probability draw number 3, and then draw number 4, and the result is the result of multiplication of these 4 numbers. Now, in the solution, you might see a different notation that I didn't discuss more precisely in the discussions that we have in previous sessions. When we wanted to define the probability of having different flavor, for example, different flavor in draw 3, in the solution, we use a terminology like that, and we call it, okay, this means that we picking a different flavor in the first 3 draw. Okay, or we pick a different flavor for the third draw, okay, considering that the first 2 are already picked in a different flavor. Is that clear? Now, this terminology, this kind of probability, we call it conditional probability. We are going to go deep into that conditional probability after the midterm. This is going to be the third chapter of our discussion. Okay, conditional probability. But I wanted to introduce the concept of the conditional probability. Okay, this notation means that what is the probability that the event D3 happened? Event D3 is going to be picking the third draw with a different flavor as the other two. Okay, this terminology means what is the probability of D3 happen if, that line means if, we already know that D1 and D2 already happened. So in this notation, happening of D1 and D2 are not under the question. They already happened. Now, if we assume that they already happened, what is the chance of D3 to happen? Now, look at the tree diagram that we had. When we had our first draw, in our tree diagram, we had two branches. Either we pick different type of candy, which is the branch that we call it D2, or we pick similar flavor with the first draw, which is the branch that we call it S2. Right? Now, in this question, because we only were kind of like interested in the different flavors, we didn't complete our tree graph, okay, the branches in our tree graph, considering if the second draw is similar taste. We know that in our probability, we could have similar pick, okay? So if we wanted to like have all the possible events that could happen on that four draw of candies, there are going to be some branches out of these S's, right? When we talk about conditional probability, okay, now look at what the conditional probability did to our probabilities. When we are here and we're considering that D1 and D2 happened, okay, we basically eliminate all the elements that are going to branch out in our universe from S2. Make sense? So if our universe was a sample space, what this specific conditional probability did is to eliminate a part of sample space. So it shrinked our possible outcome. Does that make sense? I just wanted to like give you the intuition of the conditional probability. So in the conditional probability is the similar case as we talk about in part B. And it means that we wanted to like find the probability of a certain event considering another event is already happened. Is that clear? The concept of the conditional probability and the definition of this notation. Is there any question about that? We are going to discuss in detail and how to calculate and how to use that and what is the significance of conditional probability in actual engineering technologies, which basically, by the way, filters our conditional probability. Okay, so they follow these rules. They develop based on this rule. Okay, so we are going to discuss that. Okay, but if you have any questions so far, please feel free to ask. Okay. No? Okay. Now, as your friend mentioned, another way to solve problem B, part B, is to use the permutation, right? Basically, what we wanted to like do here is a permutation of 4. We wanted to have 4 different candies, Okay, so it's a 4 permutation. The number of possible ways that we could draw candy without any condition is 12 chosen 4, which we know basically is going to be 12 factorial over 12 minus 4 factorial, which is 8 factorial. These are all the possible outcome of having a random 4 draw out of that 12 candy, regardless of any condition. Now, if we want to have the number of different draw, we have 4 sequence of test, 4 sequence of draw. How many choice we have in first draw? 12, right? Here. How many choice we have on second draw if we wanted to like be consistent with the condition of having different flavors? We have 9 choice because one of the flavors is already out of our interest, right? So we have 9 choice. Third draw would be 6 choice, and this fourth draw is with 3 choice. So we have 12 multiplied by 9 multiplied by 6 multiplied by 3 different possible way to choose 4 flavors within our basket, and the total number of choosing any 4 flavor, any combination of 4 candy, is that 12 chosen 4, 12 factorial or 8 factorial. So using the permutation and binomial coefficients, we could basically calculate the probability of our event using the number of ways that 4 flavor could happen divided by all the possible combination of drawing 4 candy out of 12, which if you do the calculation is going to be the same result as the true die. Is that clear? How we use that binomial coefficient of permutation to solve this? Are we good?
How do you know when to use it?
When you want to like count the combination of different, you want to count the different combination of a certain element, it's always involving a binomial coefficient or multinomial coefficient based on if you are allowed to repeat the elements or not. Here we didn't allow to repeat, so it's binomial. Okay, so basically anywhere that it asks you to how many configuration you could choose n k element out of n element, your mind should straightly go to the binomial coefficient or multinomial coefficient based on the condition of the elements. Okay, but in this situation, we had an easier way. That tree diagram, okay, was an easier way to solve the question. So we first went that way, but the easiest way, the proper way, is to use the permutation. Did I answer your question? Yeah. Any other question? No? Okay. Part C. In part C, we define event F2, and we define it in a way that we have exactly, when we draw 4 flavor, the result is exactly 2 pieces of 2 different flavor. Is that make sense, the condition? So we draw 4 out of that 12. We want to calculate the probability of having exactly 2 of 2 different flavors. Okay? So it's not 2 different flavor or having 2 from from one and any combination for other three flavors. Okay, so exactly two for two flavor. Two cherry, two lemon, two cherry, two orange, two berry, two lemon, something like that. Okay. Now, when you wanted to like pick this, it's the question typically shows you how to calculate. First, like let's go through the question. It wanted you to calculate having two flavor and then two piece for each flavor. So a step by step. Your first choice is to say, okay, I have four flavor. How many combination I could have that in the result I would have two flavor. So basically, out of the four flavor that you have in the first step, you have to count the combination, how many combination you could pick two flavor out of that four flavor. Does that make sense? Okay, so what is the result? Is going to be 4 chosen 2. 4 factorial over 4 minus 2 factorial. Okay, so the first step is to count the combination that you could have two flavor. Now that we have two flavor, okay, now how many choice, how many way I could pick two candy from the flavor 1. Now I have two flavor. Each of them have 3 elements, but I need 2 out of each. Okay, so how many way I could pick, I could draw 2 candy like out of the 3 candy of the first flavor that I chose. Right? Is 3 choose 2, which means 3 factorial over 3 minus 2 factorial. Okay, so this is the first step. In the second step, you calculate how many combination, how many ways you have to pick 2 out of that each flavor. And you have 2 flavor. So you have 2 situation that you have to pick 2 out of 3. Is that clear? So you pick 2 flavor and you pick 2 out of the first flavor and you pick 2 out of the second flavor. What you should do with the number? Multiply. Does that make sense? This is the terminology that I'm talking about. Okay, so the number of the ways that you could achieve that condition is n1 multiply n2 multiply n3. But what is the probability of that? All those possible ways divided by the total number of picking 4 candy out of the 12 candy that we have, which was the 12 factorial over 12 minus 4 factorial. Does that make sense? So this way, you could calculate having exactly 2 candy of 2 flavor. Are we clear on that? Please pay attention to the terminology. Each word have like a huge weight on how you have to like approach to the solution, okay? If you don't have any question, I want to move on to the question number 7. No? Question number 7 is one of the fun questions in this homework. It says that we have a basketball team, okay? And in our team, we have 3 players that only could play as a center, okay? We have 4 players that could only play as forward, and we have 4 players that could only play as guard, okay? And we have 1 player that could swing between forward and guard. So 3 center, 3 forward, 3 guard, and 1 person that only could be swing either in forward or in guard. Now, the question asks you that the coach wanted to like start the lineup, and it wants to have 1 center. Okay, these are the important part. Let me mark them. The lineup should have 1 center, 2 forward, and 2 guard. Between all the possible choices that the coach has within the player that he has, okay, how many the coach has, how many combinations we could have to choose to create the lineup with 1 center, 2 forward, and 2 guard. Now, in order to tackle this question, the easy way is to use the lineups as a free spot. These are centers. Oh, these are guards, forward, and centers. Why I'm doing that? Centers. So we need 1 center, 2 forward, and 2 guard. 2 guard. Okay. Choosing centers are easy because the only option that we have is the category of the players that are trained to be center. Okay, but when we want to choose the forwards and guards, now the coach has freedom to choose either from the, like for the guard, either from the players that are purely trained to be guard, or it could choose swingman as one of the guards. Make sense? Same goes for the forward. So the coach has 2 options for the forwards. Either choose from the category of forward or reserve one of the spots for forward, fill it with the swingman, and fill the other one from the category of the players that train to be forward. Okay? Now, considering that condition, how many type of choice based on the swingman, regarding the swingman, the coach has? 3 type of choice. Either the coach could not use the swingman, it could choose the swingman as forward, or it could choose the swingman as guard, right? Are we agree? So, if we don't choose the swingman, how many possible way we could choose 2 guard from the 4 people that we have? 4 choose 2, right? So this is the chance that we could like place and fill the positions for guards. How many choices we have for filling the position for forward? Again, we have 4 people in our category. We want to choose 2, so it's 4 choose 2. For the center, we want 1 out of the 3 people that we have, so it's 3 chose 1. Now, if we reserve 1 of the forward spot for the swingman, now what happens? Now, 1 of the spot is filled by the swingman. How many choice we have to fill out the guards in here? Similar to the previous one. we need to pick 2 out of the 4 people that we have. So it's 4 chose 2. How many we have, how many chance we have, how many choice we have for picking the forwards? 4 chose 1, because one of the spots for forward is already filled with swingman, right? So here we have to choose 1 out of the 4 people for forward. Center would not make any difference. We still have 3 people that we want to choose 1 out of them. Same analogy goes for the guard. If the swingman is occupying one of the slot for the guards, one of the position, then you have 4 chosen 1 combination to choose the other to fill the other position, the other guard position. You have 4 choice 2 to fill up the forwards and 3 choice 1 for the centers. Okay, so what is the probability in each condition? Multiplication, because this is sequence of choices. So this probability here is the multiplication of these combinations. There's a number of combinations that you could line up in this condition. Same goes with that one, and same goes with the first condition. Now, what is the relation between these 3 conditions? It's the or condition, because the coach could use the swingman as guard, or could use the swingman as forward, or could not use at all. So it's gonna be the summation of the 3. Make sense? So we have 3 conditions. The overall situation is the summation of the 3, and each of them, based on what we discussed, had a certain number of combinations that you could choose people to fill those positions out of the available player that you have. And you could calculate the total. Any question about this a specific problem, or how we run that solution? No? Okay. Question 8. This one is quite good. Question 8 says that imagine you are driving to the work each day, and in your way you encounter a traffic light. There is a chance that when you encounter that light, it would be green, which the chance is 7/16 here. It could be red with the same chance, or it could be yellow with 1/8. These are the chances. Okay? Now, let's say you observe the traffic light for 5 days, considering that these 5 results are independent, so they don't affect each other. The probability remains the same each day. The question asks you that what is the probability that you would face on those 5 days, you would face 2 green lights, 1 yellow light, and 2 red lights. This is the first part of the question. How we could calculate that? Using the terminology, I wanted to see what your kind of like instinct when you read this type of question. You have you wanted to like pick a certain combination out of your sample space. Okay, so its permutation. But you have within your choices, which is 5, you have 3 categories that could repeat, right? So your instinct instantly should say that, okay, this is multinomial coefficient. Do you see what I mean by using the question to instantly find where you should go? Now, let's move on to the solution to the first part so we know what we're talking about. You have 5 observations and you want to see how many combinations you could have out of those 5 observations. So within that 5 observations, you have 2 green, 1 yellow, and 2 red. Right? You remember that Mississippi example? Same kind of situation. So the number of combinations that we could have out of these 3 categories, each of them has a certain amount of repeat, and we wanted to like create a 5 elements out of those categories, is going to be the multinomial of these numbers, which is 5 factorial over k1 factorial, k2 factorial, k3 factorial, k1, k2, k3. Do you recall the formula in the discussion that we have? And this is the n factorial. Now, this is all the combination that you could make if you have 5 observations with green is repeated 2 times, red is repeated 2 times, and yellow is repeated 1 time. Okay? So, but that's not the probability. It's the number of the ways that you could arrange the element. Okay? Now, you have the number of the ways. At the same time, your probability should happen. So you want 2 green light. What was the probability of having green light? 7 over 16. You want 2 of them. Okay? The first one and the second one. What that means? Multiplication and. So these are the number of combination. In these combination, I have the first green light, 7 over 16, and the second one to the power of 2, and 1 yellow light, and multiply by 1 over 8, and the first red light, 7 over 16, and the second red light to the power of 2. Make sense? So this way, you could calculate the probability of our desired condition. Is that clear how we get that? The step by step? And how we kind of like analyze the situation? Are we good on that? Okay. Now, the second part asked us that what is the probability if the number of the green lights and the number of red lights are similar out of that 5 observation. Okay, you have 5 choices, and those choices could be in 3 categories. What are the conditions that number of green light and number of red lights are similar? Either we have 2 green light, 2 red light, 1 yellow, right? Or we have 1 green, 1 red, and 3 yellow. Or we had 0 green, 0 red, and 5 yellow. We can't have more than that. Because if we have 3 green, our condition says you have to have 3 red, which is more than our observation already. So this is all the possible scenarios that could happen. Either this one happened, A1, A2, A3, or this one happened, or this one happened. So what is the relation between these conditions? Summation. Whatever probability each of them has, the overall is the summation of all three because they have or condition between them. Now, let's move on to each of them. If we have one green, one red, three yellow, same concept as we talked about in the first part. It's going to be n factorial, 5 factorial, k1, k2, k3. Do you see that? And we have one green, one red, three yellow as the probability. Plus the second option, 2 green, 2 red, 1 yellow, plus the third option, which is 0 green, 0 red, 5 yellow. And we add them together and we have our final answer. Are we clear on that? Okay, we are running out of the time. I would continue the question number 9 and the other example for the extra examples in the next session. So we are going to get prepared for that. If you did not mark your attendance, please don't forget that. The attendance sheet is here. And have a good rest of the day.